folks, this is Matty Grimm again with the third part of Replication 1A of Baller et al. In GeoDa and GeoDa Space. Again, just a reminder that I assume you've downloaded the software, GeoDa and GeoDa Space, and that you've also downloaded all of the data from Blackboard into a single folder, your working directory, on the machine on which you're working. So in the first video we covered the LISA cluster maps. In the second video we covered the next two steps, Table 1 and Table 2, the simple OLS non-spatial regression and the diagnostics of coefficient stability. We are now going to cover the results reported in Table 3 and Table 4, the explicitly spatial regressions, specifically the spatial lag regressions in the southern counties and the spatial error regressions in the non-south. Again, I'm going to be moving quickly through here, just trying to work through the mechanics of the replication, and we should talk about this in much greater detail when we meet in person next week. So let's go ahead with Table 3. I'm just recalling what Table 3 reports from page 580 in Baller et al. Based on the diagnostics that indicated that some different spatial processes were at work, Baller et al. Run spatial lag models in the 1,400 or so southern counties, and then run spatial error models in the 1,600, 1,700 or so counties in the non-south. One of those diagnostics was the spatial chow test that we already saw that seemed to indicate that there was something different going on in the relationships of interest in the southern counties and in the non-south counties. And we're going to do one more test here as we get started. So let's get started with Table 3. Actually, let's redo the spatial chow test with GeoDa Space. So this is, I'm pulling up GeoDa Space here. This is the same regression that we had before that led us to look at the spatial chow diagnostics. But now let's add weights here, and we just want to grab the 10 nearest here and run the regression, or run the test here. Again, as I mentioned earlier, in GeoDa Space and in GeoDa, if you run multiple analyses, it'll append the results to the bottom, so just make sure you go all the way down to the bottom and then scroll back up to find the last one that you ran. So here's regime 1, and we want to get up to regime 0. So this is our latest analysis. So here we see again the earlier regression that we saw, or the earlier analysis that we saw, regime 1, the earlier analysis that we saw. The thing that has been added now by adding the spatial weights that was not reported before are these diagnostics of spatial dependence by regime, right? So this is for the non-south, and then down here we see for the south. And then at the bottom below the spatial chow test, we have the diagnostics of the spatial processes for the entire sample. So what is this telling us? We'll talk about this again in much greater detail in class, but basically there are the Lagrange multiplier tests help us to identify whether a spatial lag process best fits the data or a spatial error process best fits the data. If the simple Lagrange multiplier lag test, this first one here, is statistically significant, it's an indication that a spatial lag process fits the data. However, if the error test is also significant, as it is here, if they're both significant, then you want to move to the robust versions of both tests. So all of these tests are reported here, and you see the robust lag and the robust error test. And here, the robust error test is not significant, so only the lag test is significant. So at least in this diagnostic test, in the non-south, it looks like a lag process best fits the non-south, which is not exactly what Baller et al. Well, it is what Baller et al. Found for 1960. If you move over here to the right to table 4, you'll see that they find a spatial lag process, right? Or they model a spatial lag process in 1960, but not in 1970. So let's just look at that for 1970. Let's run this again for 1970 to see if we see that difference. Let's come up here. Homicide rate 1970, and let's bring all. If you double click on them, it brings them out. So now let's bring resource deprivation 1970, population structure 1970, median age 1970, divorce 1970, unemployment rate 1970. The regime variable is the same. We can close this. The spatial weights are the same. We've changed our covariates. We've changed our dependent variable. The regime variable remains the same. So let's try this again. Again, we need to scroll all the way down to the bottom and working our way back up here. We want to start here. So working our way down, here's our spatial tests. And here we see what Baller et al. Found, right? Looking at the simple versions of both tests, the Lagrange multiplier error and lag, we see that they are both significant. But then when we look at the robust versions of both, we see that the robust lag test is not significant, leaving only the robust error test to be significant. And this is ultimately what they find in the rest of the decennial years, leading them to model the error process in the non-south from 1970 forward. Meanwhile, in the south, we see that essentially the opposite is true. I mean, all of the statistics remain significant, but the robust error test has no longer, oh, excuse me, this is the global one. We want spatial dependence up here for the south. All of them are significant except the robust error. So if you look first at the simple tests, lag and error, they're both significant, so you move to the robust tests. And among the robust tests, only the robust lag version is statistically significant. So this supports the motivation in Baller et al., right? That they find a lag process best defines what's happening in the data in the southern counties, while an error process appears to be defining best defining what's going on in the non-southern counties. So with that in mind, let's then now go back to, I'm not going to save these, nope. Let's just go back to GeoDa, to our basic GeoDa. And here, let's specify the models in table 3. I'll just do 1960 and we'll let you play with the rest. So again, if we bring up our toolbar from GeoDa, go to methods, oh, we have to load our data, sorry. So I'm going to load the new project here and click on the folder icon again to load the new project. Esri shapefile, just as we've done before. But now in table 3, looking over at the Baller table, It's this table 3 is for a spatial lag model only in the south, right? So looking at our data sets that you should have downloaded from Blackboard, grab the one that's only for the southern counties. As before, GeoDa automatically generates this themeless map that offers a quick confirmation that you're working with the geometry that or the geography rather that you want to be working with. Geometry, geography, I guess the polygons are geometric. So you're working with the space essentially that you want to be working with. You can leave this open if you like, or you can close it. I'm just going to close it. And now we can go to methods regression and specify our model, right? So we want homicide rates 1960, resource deprivation 1960, population structure 1960, median age 1960, divorce 1960, and unemployment rates 1960. So dependent variable or independent variables, make sure all the years are the same. We leave the region dummy out now, right, because we're only working in the south. But now we do want our weights file to be specified. If you click on this W here, you can load the weights file. Select from, click on the folder icon. And again, sorry, my folder is very busy, but look for the south only 10 nearest neighbors. Here it is, south only 10 nearest neighbors, and set it as the default. Click OK. And instead of running a classic OLS model, now we want to click on the dial or the button for a spatial lag model. And we're now ready to run the model. Except we get an error message. Only symmetric weights are supported for this operation. Okay. So symmetric weights essentially means that if you have two units, unit A and unit B, if you say that unit A has unit B as a neighbor, then you have to say that unit B has unit A as a neighbor. That makes them symmetric. However, in looking at 10 nearest neighbors, that should always be the case, but in breaking up the data from the south to the non-south, we may have lost some of the neighbors that made this a symmetric data set. So there's a couple fixes that we could approach to this. We could force a symmetric spatial weights in another software program in R, but we'll talk about that more in class. For now, let's create a different weights matrix and just move forward with the analysis here. So click here on the W again to select a weights file. This time go here to create a new weights file and click on this W. And for the weights file ID variable, you could use either the polygon ID or the FIPS number, either one. Both of those are unique identifiers. Well, we'll use the unique identifier here and click on Queen contiguity and Queen 1. And we'll move forward from here. So this basic Queen contiguity is essentially borrowing a metaphor from chess. If you play chess, you know that the queen in chess can move in any direction. And basically by saying Queen 1, you're saying that for any unit A, its neighbors consist of those other units that are one neighbor away in every direction. So we have our unique unit identifier here, Queen 1, and just click Create. Save it as something south only Queen 1, south only Q1 works. I had generated this earlier, so it'll ask me to replace it. Yes. Success. And now we can close out here, set it as the default. OK. And now we should be able to run the analysis. Everything else stays the same. Let's run it. And here are our results. So again, up in the top we have some model fit statistics. In the bottom we have some diagnostics, but we're mainly concerned with this output in the center. The core results in the center of the output window. So starting with a constant, which is the intercept, we see a large positive and statistically significant constant. Large positive and statistically significant constant here. Resource deprivation, positive and statistically significant. Resource deprivation, positive and statistically significant. Population structure, small, but more importantly, not statistically significant. Population structure here, not statistically significant. And then median age, divorce, and unemployment are all statistically significant. Negative, positive, and negative. Median age, divorce, and employment, negative, positive, and negative. But only median age and divorce were reported as statistically significant by Baller et al. So in our analysis, by using the Queen1 contiguity matrix, we found a different result here, right? That unemployment has a statistically significant relationship. Unemployment rate, as the unemployment rate increases, the homicide rate decreases in the South. That's something that Baller et al. Did not find was statistically significant, at least in 1960. The more intriguing finding, though, is this top line in our output. W stands for the spatial weights matrix, so this is the lagged dependent variable. And we see it's positive and statistically significant. Here, positive and statistically significant as well. So this, in large part, this replicates the Baller et al. Finding. It's not precise in the sense that we didn't use the same weights matrix, because GeoDa registered our 10 nearest neighbors as not being symmetric. So we could try some other things in class to fix that. But basically, this is a fairly reasonable replication of Baller et al. Again, the biggest departure is the finding regarding unemployment. We find that it's statistically significant and negative. They find that it's negative but not statistically significant. So one minor departure. You could do the same for 1970, 1980, and 1990, replicating all the rest of the findings in Table 3. I won't do that here, but feel free to do so. You do not need to fix or change the spatial weights matrix anymore. You should be able to use this Queen1 contiguity spatial weights matrix. The only thing you need to do is change the dependent variable and, of course, change your independent variables here, and then click Run and compare the findings. I'd be interested if in 1970, 80, or 90 there are some small deviations like we found regarding unemployment. For now, let's stop there and move to Table 4. And Table 4 for 1960 runs a spatial lag model like we just ran. We'd like to run the spatial error model. So let's do the second model from Table 4, the model for 1970, in spatial error form. In order to do that, we need to back out of here, go back to our main toolbar from GeoDa, close out here, and then load a new data set. And now we're going to be working only with the non-southern counties. So let's load that shapefile. Again, as before, GeoDa automatically loads a themeless map, so you can confirm that you're working with the geography that you want to be working with. Here we can confirm that quickly. I'm going to close that and then bring up methods, regression, and we see our familiar interface for specifying a model. So let's run homicide rates 1970, and we want our predictors, resource deprivation, population structure, median age, divorce, and unemployment. Resource deprivation, population structure, median age, divorce, unemployment, homicide rate, all 1970. For the weights file, I imagine we're going to get the same error, so let's just generate another queen1 contiguity file. Go to create new weights file, click on the W, use the FIPS number for the unique identifier queen1. You don't need to pick anything else. Click create, save it as non-south only Q1, so non-south only Q1. I did this once before, so I need to replace it. I will. Success. And now we can close this out, keep it as your default, and click OK. So now we have our dependent variable, our independent variables. We have our spatial weights matrix as a queen contiguity. Again, this is not the 10 nearest neighbors that bother at all, but we're trying to work around this symmetric matrix error that GeoDa gives. And now let's click on spatial error model for 1970, and we can run. Here's our familiar output window, model fit statistics on the top, diagnostics on the bottom, and our core output of interest in the middle. Let's do a quick comparison here. Resource deprivation, well, you can see it's positive and statistically significant, positive and statistically significant. Population structure, positive and statistically significant. The magnitude of population structure, its effect is slightly smaller than resource deprivation, so we can see that as well. Median age, negative and statistically significant. Median age, negative and statistically significant, very close. Divorce, positive and statistically significant, and in Baller, the same. And unemployment, we find, is not statistically significant, and unemployment, they find, is not statistically significant. I'm sorry, I was looking at the 1960 model. 1970, and positive, positive, negative, positive, 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 negative, positive, all significant. Unemployment in 1970, negative and not statistically significant, negative and not statistically significant. So this is a nice replication, nicer replication than with the previous model that we did. Lambda is the coefficient for the spatial error term, and this is positive and statistically significant. And here we see a positive coefficient. It's not clearly labeled as significant or not, but I would find it very. I don't quite understand why they didn't do that. Looks like there's at least another line of data missing in table 4 here, and the coefficients weren't labeled as significant. I'm not quite sure why they did that. I find it very hard to believe that the spatial error term is not statistically significant, especially given their analytic emphasis on it. So that looks like just a typo, which is interesting. 3 typos in a row, I guess, in a key finding. But anyhow, in our results, we find positive and statistically significant. So again, this is a nice replication. Setting aside the difference in the spatial weights matrix, this is a nice replication of model 2 for 1970 in table 4. Please play more with the 1980 model and the 1990 model. See if you can replicate those findings using the same methods that we just used. Here in GeoDa, you'll just need to change the dependent variable and the independent variables. You can leave the spatial weights matrix as is and leave the spatial error as is. and just keep running the new model as you change the dependent variable and the explanatory variables. Keep in mind that every time you run, it's going to append the results to the bottom of your last run. So just make sure that you're scrolling down to find the appropriate results. And that's it. That's table 4, and that's the last set of reported results from Baller et al. So that completes our replication for this piece. Thank you.